So the first part of the opener here, we're just doing what we've done before. We did this on Monday. But then the second part, this is actually what we're getting into today. We're going to be talking about square roots. So this is kind of an introduction to it. Hopefully this part of it is something that's a little bit familiar to you. So for each one of these, we're going to write the prime factorization in standard form. We're going to write it in exponential form. To do that, what are we going to do? We're going to make a factor tree. So let's start with the 60. 60 ends in a 0, so what do I know has to go into it? 10. So I could do 10 and 6. Did anybody do it a different way for 60? You could do 12 and 5 if you wanted to. You could do 2 and 30 if you wanted to. You could do 3 and 20. Any one of those will work. Any one of those will give you the same answer as long as you do it correctly. But I like the 10 because it ends in a 0. Anytime it ends in a 0, I always start with the 10. What goes into 10? What do we multiply to get 10? 2 and 5. All right, those two are both prime, so we'll circle them. 6 is composite, meaning it's not prime, so we can factor it. What do we multiply to get 6? 2 and 3. All right, and both of those are prime, so we're done, right? Or at least we're done with the factor tree. Now, we want to write it in standard form. I didn't leave myself enough room up top here, so I'm going to just write the standard form underneath. Standard form would be what? 2 times 2 times 3. Okay, so we wrote those numbers in what order? Least to greatest. So we've got 2 times 2 times 3 times 5. Not a bad idea to just check them off as you get them so you can look at your factor tree and make sure you have everything. And that's it, right? Okay, how about the exponential form? What's that going to look like? 2 to the second power, because there's 2 2's, right? Times 3 times 5. All right, so that's a perfectly acceptable exponential form. If we wanted exponents on all of these numbers, then what exponent would we put on the 3 and the 5? Okay, so this 1 here, you can put there if you want, but you don't need. All right, when it's exponential form, some people like to put an exponent on every one of them. So if you want to do that, you would put 1s on the ones where there's only one factor. And that's it, right? That one was pretty easy. Let's do the 45. What do we multiply to get 45? 9 times 5, okay. 5 is prime, right? What about 9? Is that prime? No, we can keep factoring that. What do we multiply to get 9? 3 times 3. So the standard form then is going to be what? Okay, so 3 times 3 times 5. And the exponential form? Yeah, 3 to the second power, which we would read that as 3. What's another way of saying 3 to the second power? 3 squared, exactly. So 3 squared times 5. And again, if you want to put the exponent on the 5, that's going to be a 1. So off the top of my head, I don't really know two numbers that multiply to get 128, except I know 128 is even. So what does that tell me? What number has to go into it? 4. If 4 does go into it, but what number, because it's even, what number has to go into it? 2, right? So if you use 4, that'll work. But I don't know for sure that 4 goes into it until I get started here. So I'm going to do 2. And I know 2 has to because it's even. Now, how do I figure out what I multiply by 2 to get 128? Yeah, you divide. So just punch into your calculator 128 divided by 2. And you get 64. Now, 64 is also even. So if we wanted to, we could divide by 2 again. Although 64 is a number that we know. What numbers do we know multiply to get 64? 8 times 8, right? So I like using 8 times 8 mostly because it's going to make our tree a little bit shorter. If we just kept going by 2s, we're going to keep going down pretty far. But it really doesn't matter which way we do it. We have 8 times 8. Each one of those 8s is composite, right? We can factor those and get what? 2 times 4. And the 2's are prime, but the 4's are going to keep going. So each of those 4's is going to be 2 times 2. Now, here's a good example of why circling the prime numbers is really useful. What a lot of people will do here is see all these 2's down here at the bottom, see all these, and then forget about this one. But since we circled it, it's going to draw our eyes back to it. It's going to make sure that we remember to go back and use that one also. So when we do our standard form, we're going to have how many 2's? 1, 2, 3, 4, 5, 6, 7. I agree. So 2 times 2 times 2 times 2 times 2 times 2 times 2. Man, that's fun, isn't it? Right now it's 7 2's. So the exponential form is going to be a lot quicker, right? What's that going to look like? 2 to the 7th power, and that's it. This is a really good example of where the exponential form saves us a lot of time in writing, right? Okay, so the exponential form, much simpler here.
I used 4 on 128, got the same answer.
So how about 1,000? Yeah, 1,000 ends in 0, right? So if we divide by 10, we're just taking one of the zeros off, and what's left? 100. And then I'm going to do the 100 first. 100 is 10 times 10. All right, we still don't have any prime numbers, though, because we have a bunch of 10's here at the bottom of our branches. So we're going to need to do what times what for each of those 10's? 2 times 5. And the 2 and the 5, those are both prime, right? So when we do the 2 times 5 for each of those, we'll circle them. And so we've got 2 times 5 there and 2 times 5 there. All right, so standard form. Let's see if I have enough room for this. How many 2's do I have?
3.
I've got 1, 2, 3 of them. So 1, 2, 3. So 2 times 2 times 2 times 3 5's. Okay, so no 3's, so we'll skip over that. We've got 5's now. So 5 times 5 times 5. And that's it, right? That's everything?
No.
Yeah, I mean, for the standard form, that's everything, right? Okay, so we've got them all marked. But the exponential form we still need to do. So exponential form, what are we going to get? 2 to the third power, or we could say 2 cubed times 5 to the third power, or 5 cubed. Okay, another good example where writing the exponential form's a lot simpler. So not only does the exponential form take less time to write, but it's also easier to see how many of each number there is. So like looking at this one, for example, if you just look at this big list of 2's, you would have to count them to know that there's 7 of them. Okay, because you can't just look at it and say, yeah, that's 7. Okay, you'd have to go through and count. But doing the exponential form, 2 to the 7th power, you know there's 7 2's there. Okay, it makes it really easy. You don't have to count anything, and it just looks a lot simpler. We are going to use the standard form more often when we're doing stuff with square roots than the exponential form. So even when we get something like this, 2 times 2 times 2 times 2 times 2 times 2, however many times, we're going to write it out in the standard form most of the time because that's going to be helpful when we're doing the square roots. So speaking of square roots, this square root of 81 means we're looking for a number that does what?
Multiplies by itself.
Multiplies by itself to get the number 81, right? So we're looking for a number that multiplies by itself to get 81. All right, so what number multiplies by itself to get 81? 9. So that's equal to 9. That's all you have to do. Okay, I am going to show you something else real quick, but that's all we need to do right now. Okay, how about the square root of 36? What number multiplies by itself to get 36? All right, 6. Okay, now to do this one, I'm going to go back and do these two a slightly different way. So we're looking for a number that multiplies by itself to get 81. So 81 is what times what? 9 times 9, right? So the square root of 81 is the same thing as the square root of 9 times 9. You guys agree with that?
Yeah.
Okay. Well, this, 9 times 9, what's another way of writing 9 times 9? 9 to the second power, or 9 squared. Okay? So, the square root of 81 is the same thing as the square root of 9 times 9, which is the square root of 9 squared. And the square root of 9 squared, we said, is 9. Okay, let me do that with this one real quick. So the square root of 36 is the same thing as the square root of 6 times 6, which is the same thing as 6 squared. So this is just saying that it's 6 times 6 to get, we're taking the square root of 6 times 6, and we get 6. So what do you think the square root of 31 squared is? What did you say, Trey, again? 31. We don't have to do any math, really, because the square root of 31 squared is just 31 times 31, right? Well, what number do you multiply by itself to get 31 times 31? What number do you multiply by itself to get 31 times 31? 31, right? We're already multiplying it by itself. So that's actually the easiest one here because we don't have to do any math. What's happening is the square right here and the square root right here are canceling each other out. So in this one right here with the 9s, the square and the square root cancel each other out, and that just leaves the 9. Okay, in this one right here, the square and the square root cancel each other out, and that just leaves the 6. Okay, in this one right here, the square and the square root cancel each other out, and that leaves us the 31. We'll talk more about that today with the notes. But first of all, before we do that, square root of 50. Is there a number that multiplies by itself to get 50? I mean, so 6 times 6 doesn't work. That would give us 36, right? 7 times 7 would be what? 49. That doesn't work. 8 times 8 would give us 64. That doesn't work. And now we're getting numbers that are bigger than 50, so anything bigger than 8 is not going to work either. So which one's the closest? 7 times 7 is pretty close, right? So 7 times 7 would give us 49. So if we're taking the square root here, we're looking for a number that multiplies by itself to get 50, we would be really close if we said it was 7, because the square root of 49 would be 7. So what do we know about this square root? It's going to be really close to... It's going to be really close to what? 7. Since this is really close to 49, the square root of 50 is going to be really close to 7. It's actually going to be a little bit, would it be bigger or smaller than 7? It would be a little bit bigger, right? Since 50 is a little bit bigger than 49, then the square root of 50 is going to be a little bit bigger than the square root of 49, which would be 7. Okay, so does anybody know what this symbol right here means? The approximately equal to? I just said it. I just called it. Yeah, it means approximately equal to. So it's like an equal sign, but it's squiggly instead of straight. And it means that it's close to. It's approximately equal to, but not exactly. So there are a lot of square roots that we can't solve. We can't figure out what the square root of 50 is exactly. It's actually what we call an irrational number. But we can figure out what it's close to. And actually, if you punch it into your calculator, right now, if you punch in 50 and then hit the square root button, what would it say? What does it say? 7.07. So it's really close to 7, right?